So welcome back to the mock exam. This is part 2 of my commentary on the questions. But because of its importance, let me repeat the legal question 1. I affirm that I will not give or receive any unauthorised help on this exam and that all work will be my own. True. Now we're going to jump to question 12 because we did questions 2 to 11 in part 1. So I have to wait for this to load. Now remember that questions 12 to 21 correspond in fact to section B of the May 2019 exam. Now the point about this question, graph finally appeared, is that you have to notice that we're looking for the false statement. We have 5 statements, for which only one is false. So you have to read carefully here. Of course, you'll have discovered that that's what we want if you look at at least 2 of these questions. But if you just choose the first one that's true and move on, you'd have got this question wrong. Anyway, these 5 statements can appear in any order. So the first one, let's just start from the top. The first one, G is a planar graph. Is that true or false? We're looking for the false statement. So the chances are the first one will not be false. In fact, G is a planar graph because although at first sight we have these unauthorized crossings, if you like, we have 2 edges crossing not in a vertex, we know very well that we can just sort of take this triangle here and make it smaller so it fits inside the other triangle. That will eliminate this crossing. Or if you like, we can just pull this edge on the outside and that would also eliminate the crossing. We can do the same on the right hand side. So the fact of the matter is that G is a planar graph. That's a true statement. I've learned to do arrows. So that's a true statement. Now, G has at least 3 distinct Eulerian trails starting and ending at V1. So what is a Eulerian trail? An Eulerian trail, it's one which covers each edge exactly once. You're allowed to go back to vertices, but you can't go twice over the same edge. Now, in this graph, all the vertices have degree 2 or 4. They're all even degrees. So there is an Eulerian trail. So the question is, how many are there? Or are there at least 3? Well, the answer is yes, because you can start by, of course, I mean, we don't know if we're talking about ones with arrows. We don't really have arrows, so it doesn't. Let's see what we do when we could go from V1 to V8. But the point here is we really have 3 choices already at vertex V8, because we could go down this way, we could go down this way, or we could go along that way. And those will all be viable choices because these 3 edges have to be covered somehow, and we're going to end up at V8 even if we don't start there. So I mean, I don't have to continue because there will be ways of continuing. For example, I could go down there and across there, or I could go down there and then back up there and across there, or I could go straight down and come back later to V8. So there are certainly at least 3 distinct Eulerian trails. So the answer to the, I've rubbed that out by mistake, but it doesn't matter. The answer to the first one we said was true. So that's true. The answer to the second one is true. Now we're coming to the third question. The walk, V1 to V8 to V2 to V3 to V4 to V5 to V7, V4. So we're allowed to go back to the same vertex as long as we don't go over an edge more than once. V5. V7, maybe I've done that before. Let me start again. Sometimes you do get in a mess. V1, V8, V1, V8. Oh, I'm not doing so well. V1, V1, V8, V2, V3, V4, V5, V7, V4, that's allowed, V6, V7, it's allowed, because I haven't repeated any edge more than once, V8, V1, but now I am repeating an edge, and I've left one edge out. So this is wrong. This is not a closed Eulerian trail. So in fact, the correct answer this time is that this one is the false one. Okay, so we could actually move on. I mean, you actually see that immediately because there's V1, V8 here, and there's V8, V1 there. Those edges are repeated. Okay, so that is the correct answer, but let me just explain the other two in case these had come up in a different order or in case you looked at those first. G is, these should therefore both be true, in fact they are. G is Eulerian. Well, I've explained that's true because all the vertices have even degree. If we remove the edge V3, V4, okay, so that's this edge here, if we remove that, what have we done? We've replaced two vertices of degree 4 with two vertices of degree 3, but there will still be a semi-Eulerian trail. So that is actually okay, that's the correct answer. Okay, so this is correct. As it has to be. The last one, any plane drawing of a graph with 8 vertices and 12 edges must have 6 faces. That's the regions, including the outside. Well, that's true because that's Euler's formula. 8 minus 12 plus 6 is plus 2. So that is correct. Now, as it stands, we don't have a plane drawing, but if I were to make the modifications which I suggested, we would have a plane drawing, and we would find that there were 6 faces. So you can check that. Okay, in any case, there was just one false statement here. Let's go on to the next page. Next question, I should say. Right, so here it's not the same question, it's a different question. We've got the same graph, but different statements. And this one, this time, we are looking for the true statement. So we're looking for the one statement that's true. So if we're lucky, we find this straight away. And as it turns out, the first statement here is, in fact, true. It's probably the hardest one to check. But anyway, if the two edges 3, 8, so that's 3, 8, these two vertical ones are being removed, and 4, 7. The resulting graph is bipartite. Is that true? Well, if we remove this edge on the left, you see this sort of cross, this part of the graph here is K22. We've got 2 vertices here, 2 vertices there, and the 4 edges joining them, any vertex to any vertex. And this is certainly bipartite, this bit here. Or bipartite, the same way of saying bipartite is that we can just colour the vertices with 2 colours. So we could, for example, take alpha here, because these are not adjacent. This has to be beta, this has to be beta. But now if we continue, this can be alpha, this can be alpha, and this can be beta, and this can be beta, because again, this part here is bipartite. And they join together. So in fact, this statement here is true. So that is the correct answer. And we can move on because we're only looking for the true statement this time. But briefly, let me explain the others. Why are the others all false? G is not Hamiltonian because Hamiltonian means there's a Hamiltonian cycle. So there's a cycle that goes through every vertex. exactly once. A closed path that goes through every vertex, well, as the path has to, exactly once. So you see, the problem is we can start at V1, go to V8, but then wherever we go, we've got to come back through V8. So we can't, you see, we've got to go to V2. We're forced to visit vertex V2, but if we visit vertex V2, we've got to come to it from V8 or leave it using V3 and V8. But then we've got to go through these vertices more than once. Okay, so because we've got to also get to V1, so we're going to have to go through more than once. So this is not Hamiltonian. The chromatic number is the maximum of its vertex degrees. Well, the maximum vertex degree is 4, but even if I replace these vertical edges, we would be able to colour it in 3 colours. Okay, because we could have alpha, alpha there, we would need a gamma here because these would become adjacent. So we would have beta, gamma, but then we could have gamma, beta, and we could colour the whole thing in 3 colours, which is less than the maximum of the vertex degrees. So this is false. G has exactly two 6 cycles. Well, that's wrong because here's 1 6 cycle, this sort of trapezium here. But I could also make it a parallelogram instead, and there are two with the other sort of symmetries, one upside down and so on. So there are at least 4 6 cycles. So this is false. 4 distinct pairs of edges which when removed disconnect G. Well, that's also wrong because in fact we have, see, if I get rid of these 2 edges here, I've isolated this vertex, so that will give me a disconnected graph. But then there are 4 such vertices I could isolate. That would give me 4 pairs of edges. But I could also eliminate these 2 edges. That would be another pair of edges which, when eliminated, disconnects the graph. So there are at least 5 distinct pairs of edges which do this job. So all these statements are false. Okay, let's go on. So that dispenses hopefully with that graph. Now, there's something more about graphs, but this is more a question about colouring, counting colourings, which remember was on an early part of the course when we did recurrence relations. This doesn't have much to do with, well, it does because there's a derangement involved. So here we have the sort of question where we have to work out whether these statements are true or false. We don't necessarily need to know every single one. We may be lucky and be able to answer the question with just knowing some of these, the truth or falsehood of some of these statements. So let's start and see what we can say. So we have K4. So K4 is the complete graph with 4 vertices. But let me actually draw that just to. So I can draw it really as a tetrahedron. So let's see. There we are. There's a bit of a mess up here, but that's a single vertex, obviously. That is K4. So the point is that every vertex is connected to every other vertex. That's all you need to know. So we have these 4 vertices and we have 4 colours. Now, part A, if there are only 3 colours, there is exactly one way in which the vertices can be coloured. Well, that's false because this has chromatic number 4. You know, every vertex has to have a distinct colour because otherwise, because they're all connected, any pair of vertices here is connected. So we need 4 colours. The colours are actually numbered 1 to 4, not alpha, beta, gamma, delta. But in any case, with 3 colours, we can't colour the vertices. There's no way in which we can colour the vertices in such a way that no two adjacent vertices have the same colour. So A is actually false. Wrong. Part B, if there are 4 colours, there are exactly 9 colourings with the extra restriction, blah, blah, blah. Well, without the extra restriction, there would be 4 factorial ways of actually colouring the vertices. Because these vertices and these colours are labelled, so we could give any 4 colour to the first vertex, that would leave 3 colours for the next one, and so on. There would be 24 choices. But if we can't put the colour C1 against vertex V1 and so on, we're looking for derangement of the 4 numbers 1 to 4. That's a permutation in which there's no number that stays the same. And if you've read the minimum about derangements, we spent some time on this in the lecture course, you'll know that D4, the number of derangements of 4 objects, is 9. So this is actually a true statement. So this statement here is true. B is true. Correct. Well, true. Now, what about part C? So if there are 5 colours, there are 5 factorial ways in which the vertices can be coloured. Well, that's actually correct, because you see the vertex V1, there's no restriction this time, can be coloured in 5 ways. And vertex V2 can be coloured in 4 ways. Then we have 3 colours left, and we can choose one of those for vertex V3. And then the last vertex, we have 2 colours left for that last vertex. But that is 5 factorial. You see, the fact I haven't added the 1 doesn't affect the number. It's 6 4s to 24, 120. So this is actually a correct answer. That's a correct answer. But you see, the same reasoning would tell you that D is false, because I would start with 6 and I'd go 6, 5, 4, 3, and I'll have left out the 2. So the answer is not 720 here, it should be 360. 360. So actually D is false. So where are we now? B and C are true. Do we have that? No. A and D are, so this is false as well. A and D are false. That's therefore the correct answer. A and D are false. The others are not correct, which you can go through. Okay, next question. Get rid of this. Okay, now we're on to questions about mazes and searches. Now don't panic here, you're not going to have to copy this. It shouldn't, you could copy it if you wanted to. Not too hard, it wouldn't take you that long. But I think you can probably do this by just writing down the numbers on a piece of paper. This question is about depth first searching of this maze. So we just have to select one, but we're asked again which one is false. Okay, so again we have to be careful, we're looking for the false statement, so we can't rush this sort of question, we have to look at least 2 parts to make sure we know what we're doing. Okay, well this is a depth first search, and it's been very precise instructions about how to carry this out. There are different ways of carrying out depth first searches. A computer would probably add all the vertices, but the way we've done it in this course is just to add 1 vertex at a time, and here we're asked to add the vertex with the largest label. So we can actually write out the stack. I can write it out for you here by just writing out the numbers. So we're going to start with vertex 1, which I'll call S. And we're going to add things to the stack from the right-hand side. It's a stack, that's the important thing to remember. So what we do, we add the largest the vertex with the largest label. So that means that looking at vertex 1, we have to add the 5. So we add the 5. This is an S, not a 5. We add the 5. And then you see at 5, 1 has already been visited. So we have to backtrack. We have to remove this vertex from the stack in order to get back to S. Perhaps I should call that 1. In order to get back to 1, and 1, then we can add the 2. And now we can fly away because we add the 2. We have to add the vertex with the highest degree, the highest number, so largest label. So from the 2 we can add the 7. From the 7 we can add the 11. From the 11 we can add the 15. No backtracking here. 15 we can add the 20. We have to add the 20 according to the rule. Then from the 20 we add the 21. Then we add the 17. And then adjacent to 17 there's 16 that hasn't been visited, but there's also 22 which is larger. And from the 22 we get to the finish 23. So that is what does it say? We say stop this. The search is stopped when F enters the stack. Well, F has now entered the stack. So there's the stack. We only had to remove one vertex from the stack at one point. Now, if you were to write down the corresponding tree, it would be fairly simple. It would start with vertex 1, and then at vertex 1, we went to vertex 5. But then we had to go back because 5 wasn't leading us anywhere. We went back to 1 and added 2. But once we got to 2, we were able to go to 7, and we were able to continue all the way down without going back once. So the tree looks something like that. There's only one twig, so to speak, and it has 11 vertices. Well, we can count them here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's correct. And therefore, being a tree, it has to have 10 edges. So this is a true statement. But remember, we're looking for the false statement. So this is true. Backtracking is needed on at least one occasion. Well, we explained that was true because we backtracked when we got to 5. So that was needed on one occasion. That was true. The length of the path in the resulting tree equals 8. Well, I don't think that's true because it went 1 to 2, the path, the length of the path from S to F. So that's like looking in the tree and looking at the length of this path down from 1 to 23. We forget about 5. So actually it has length 1, 2, 3, 4, 5, 6, 7, 8, 9. That's false. So this is therefore the correct answer to the quiz. The length of the path is 9, it's not 8. So the successful path passes through 15. That was correct, actually. That was a correct answer. Unfortunately, I've got no space to show you the last one, so I've got to remove all the work here. And let's just move it up, but remember the arrows are in the wrong place. The shorter this DFS search does not yield the shortest path. That is correct, because the shortest path, you see there's a shorter path. If we went the other way, it would be 1, 2, 3, 4, 5, 6, 7, 8, slightly shorter. So the 8 comes from the other path, which we didn't get. That was because we were asked to choose the largest label, actually, so this is important to follow the instructions. Anyway, the false answer is the third one here. Okay, next question, and we'll see the same graph again, and this time we have to do a breadth first search. And not only that, but we have now a selection of possible answers according to the truth and falsehood of the statement. So maybe we don't have to go through every single statement. But anyway, let me do this breadth first search. And this is harder for me because breadth first search, one would have to write down more vertices because you put them all in the queue. So I'm actually going to do this on the graph, but unfortunately, if you were to do this, you should write it down on a piece of paper. I don't think you need to copy the graph, but you would need to write down the vertices on a piece of paper. It's hard for me to do that. So I'm just going to sort of show you through this, and hopefully we'll have enough information to answer these questions. So the first one will be a matter of deciding whether the search takes us to the left or to the right in order to get to F. And we won't know that until we get to the end of the search. So let me start this by just sort of talking through what I would put in the queue, vertex by vertex. So we're starting with vertex 1. Now what we have to do is add all the unvisited vertices in the queue in increasing numerical order. So that means we do 1, and then 1 sees 2, and it sees 5, and you put them on in that order. So the queue would start, I just do the start of the queue, it would start 1, 2, 5. And then that does 1, so to speak, and we move on to 2. And 2 sees 3 and 7. You put them on in that order. 2 is adjacent to unvisited vertices 3 and 7. Okay, and that does 2. And then what's next in the queue? Well, if I don't see the numbers on the right, I have to remember that 5 is next in the queue. But 5 doesn't see anything. So 5 can get off the queue, so to speak, straight away. And we're now on to vertex number 3. Vertex number 3 sees only 8. It's the only unvisited vertex. So it sees 8, I can do that and cross off the 3. I'm not going to write any more numbers down now. Now then we have to go back to 7. You see, we're sort of switching back and forwards. When 7 was the next in the queue, we have to now remember that. So 7 sees 11. That deals with 7. But then next in the queue is 8. And 8 sees 4 and 9. They go on in that order. Then we go back to 11. 11 sees 15. And then we go back to 9. No, we go back to 4. But then we go to 9. 4 doesn't see anything else. 9 sees 13 and 14 in that order. Then we go back to 15. 15 sees both 10 and 20 in that order. Then we go back to, which is the lowest one, 13. 13 sees 12 and 18. And also 14. No, 14. Where were we? I've got lost probably already. 13. I did that. I probably had to cross off 14 at some point. So there's a slight error here, but I don't think it will affect much. So we go. Well, now of course I've lost my place. But let's think we're now at 20. So 20 sees 16 and 21. That deals with 20. So notice actually at this point that we've just done 12 and 18. And then I went jump to 20 that did 16. So we do actually see these 3 vertices in the queue adjacent in that order. That is correct. That statement is correct. Anyway, then I go back to 12. 12 comes off. 18, I can do 19 and 22. Then I go back to the 16, which sees the 17. The only unvisited one, 21 can come off. And then I go back to the 19, that comes off, but the 22 now sees the 23. Okay, so although I think I forgot to cross this off at some point, 14, the point is that our search got to F via the right-hand side because it just managed 22 we got to 22 from 18, so the search actually went through the right-hand side. So now we should have enough information to do these statements. The length of the path is equal to 8. Well, that's correct now because it's this other path, because we essentially went on the right-hand side. 1, 2, 3, 4, 5, 6, 7, 8. So that's actually a correct statement. So this is correct. I explained that this is also correct. And for a similar reason, this one is false because 16, 21, we don't see the things in this order. So this is false. Between any two, well, let's see where we are now. We've now decided 3 statements. So remember the first 2 are true. The arrows will have to make the arrows disappear now, but the first 2 are true and the third one is false. So A and B are true. They are true. So actually the first statement here is correct. So because they came in that order, well, I mean, the question's been kind, if you like, to you, because the first question, the first 2 are correct. So if you decided to check those first, you could have finished this question immediately. B is true, so B and true are not false. C and D are both true, that's wrong. What about A and D? Well, A is true, we know. So I don't actually need it. I didn't need to know much about C and D here if I'd have looked at A and B first, but let me just explain why D is actually, it doesn't matter whether D is true or false, but actually it's true. This is a sort of question you might have been asked in a different quiz. Is it true that there is a path with at most 9 edges between any 2 vertices of M? Well, one way of doing that actually is to look at there's a cycle here of length 13, a 13 cycle. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 vertices. So between any 2 vertices in this cycle, we have at most 6 edges. You can always get between any 2 with at most 6 edges. Just choose the correct way to go. But if you look at the remaining vertices outside this cycle, most of them are just a distance away from this cycle, except for vertex 5, which is a distance 2 away. So even if we wanted to get from 5 to, say, 14, we would only need 9 edges, because 2 to get to the cycle, at most 6, in fact fewer, to get round there, and then 1 more. So 6 plus 3 is 9. So this is actually, D is actually a true statement. Okay. Anyway, we didn't need that. Let's now go on to the next question. So yes, I put the correct answer here. Flows. Now you'll know that when I taught flows, I tried to make you understand, if the graph was not too complicated, to try to work out the value of a maximum flow without necessarily applying the algorithm. You can't do this if the thing is complicated, but this is not very complicated, so one can actually look visually for maximum flows, minimum cuts, and then you can check your answers with the algorithm. But you shouldn't need to do that to answer this question. In fact, the next question will be about the labelling algorithm for the same graph. So let's look at these statements here. Now this is a different sort of question. You have to be very careful because you have to decide exactly how many statements are true or false. So with this sort of question, you really have to go through every single part, and you have to do that very carefully. So in this sort of multiple choice question, we should have got to decide how many are true. And if you get the total wrong, you will get 0 marks. So, but on the other hand, the questions are fairly clear and unambiguous. So what is the value? Before we address these, we know the key theorem is that the value of a maximum flow is equal to the capacity of a minimum cut, or maximum value is equal to minimum capacity. In general, the value of any flow is less than or equal to the capacity of any cut. Only when those two numbers come together is one maximum and the other minimum. So what is the value of a maximum flow here? So if you look at this graph, it's clear that any maximum flow is going to have value less than 10. So the value of a maximum flow is less than or equal to, certainly it's less than or equal to 10, because that's the value of that's the total flow number, the total capacity, of the pipes from S, or the pipes coming into T. So the value is certainly less than or equal to 10. But it doesn't take much more inspection to see that in fact the value can't be more than 6. We can certainly get a flow of 6 because we can get 3 along the top. We only have capacities 3 and 3 here, but we can get 3 along the top and 3 along the bottom. So we can certainly flow 6 from S to T. That's a lot less than 10, but we can flow 6 from S to T. But we can't flow any more, you see, because to flow more we'd have to use the diagonal edges, but it wouldn't help us because we get stuck with these 3's. So actually the maximum flow, the maximum value, is actually equal to 6. So it's not 10, it's actually 6. Now that should also be the value of a minimum cut. So if I can find a cut with capacity 6, I'll know that's a minimum cut. And here you just have to sort of fiddle around a bit. You just have to try and cut the graph in certain ways and see what the capacity of the cut is. So for example, if you cut here, it's obviously 10. That was useless. You could maybe cut this way. If you cut that way, the value of the capacity of the cut, all the arrows are going from left to right. So actually in this case it would be 10 plus 4 plus 6 is 10 again. So the capacity of this green cut is 10, as is the capacity of this one as well. The question is, we're looking for a cut of capacity 6. Well, we can do that by cutting, let's see, if we cut this way, here we are, no, try again. If we cut this way, there we are, there's a cut with capacity 6. It has capacity 6 because 2 arrows are going backwards. Remember, the capacitor, we're looking for the arrows going from the S part to the T part. So we have capacity 3 this way, and we have capacity 3 this way. The other arrows going backwards, so they don't count. So the capacity of this pink cut is 6. So there's a cut of capacity 6. Now I think we've probably done enough to go through the questions. So the value of a maximum flow equals 8. That's wrong, because the value of a maximum flow is 6. We can't get 8. So this is wrong. Sorry. Wrong. Any flow has value less than 8. Well, that would be true because the maximum flow has value 6. So 6 is less than 8. So this is actually true. True. There exists a cut with capacity 8. Well, we haven't actually answered that, so let's leave that for the moment. Any cut has capacity greater than or equal to 8. Well, we've seen that's false because we found a cut of capacity 6. So that's false. But because of the nature of this question, we still have to decide C. So does there exist a cut with capacity 8? Well, I found one of 6, I found one of 10. Can I find one of capacity 8? Well, I think I can, because if I go down vertically here, do it with a double line so we know which one we're talking about, this cut with this double line here, the capacitors of the forward going arcs are 3 plus 2 plus 3, so that is 8. Okay, there's one arc with capacity 2 going backwards, but that capacity 4 going backwards, but that doesn't count. So there is a cut of capacity 8. So this is a true statement, and therefore there are exactly 2 true statements. So the correct answer in this case is 2 statements are true. Next page. So we have the same network, but we're asked things about the labeling algorithm. So we know now that you can check that the numbers are the same. Well, in fact, it says they're the same because the network involves the capacitors as well. So this is the same network as in the previous question. We know the maximum flow is 6. Now we're asked to apply the labeling algorithm using alphabetical order when there's a choice for putting vertices on the queue. And let me just go through these. This is where we have to find a certain combinations being true or false. So maybe we don't need to know all of the validities, but let's start with the first one, the first statement. A maximum flow is obtained from the labeling algorithm after 2 iterations. Well, given that the maximum flow is 6, not 10, one might expect that that's true, that maybe the first iteration would give you the 3 along the top, and the second one would give you the 3 along the bottom. So, but we really ought to do that because it's not obvious. So now here it's tricky for me, but I'll do the best I can here to do the labeling algorithm. So let's see, I need a bit more space, maybe there. So I'm do the best I can here. Let me do the labeling algorithm. Let's start with the first iteration, and I'm going to save space. I'm not going to write S. I'm going to write the vertex A at the top. Let's write it here. A, B, C, D, E, F. I don't know if I need to write T, but I will. Well, perhaps I should put S as well. So we're going to do the first iteration. So I need to do the Q as well. So S goes in the Q, S sees A and B in that order, alphabetical order. So S, you start with infinity there, I won't bother to write that. A, we can get 5, it's obviously coming from S. B, we can get 5 from S. That does S. Then we go to A. A can see C, which is just also top here. It can't see D because there's no flow along this edge. We're starting with 0 flow. So A only sees C, so C can go on the Q, does go on the Q, and C can get 3 from A because it can't get the 5 because the capacity is only 3 here. So I'm going to show you. So where are we? So we've done A now. Now we go to B. B can now see, can't see C because it's been visited, but B can see D. And D can get 3 obviously from B. I won't bother to write down B. That does B, but now C can see E. Can't see E, C is up here, remember, it can't see F because there's no flow on this edge. So C can see E, and E can get 3, obviously, from C. That does C. Then D can see both, it can't see E because it's been visited, D can see F, and F can get 3 from D. But it's E that we use first to get to T. So it's E that gets to T, so to speak. And so T gets a flow of 3 from E. So indeed, after the first iteration, we have simply gone along the top. Okay, to get to t. So let me just summarize that by putting the new flow numbers now on the top. So we managed to get a flow of 3 along there, 3 along there, and 3 along there, and 3 along there. If you trace back, that's what happened. So in particular, this edge is now saturated, and this edge is saturated. So now, well, we can say at this point that the value of the augmented flow after one iteration is 3. That is correct. It started as 0. It has become 3. So statement B is in fact correct. Now, but we need really to do 2 iterations, or we need to do a bit more to see what's going to happen after 2 iterations, because I want to work out A. So let's start the second iteration. Perhaps I shouldn't have rubbed out the first one. I'm not having to do this again. So S, A, B, C, D, E, F, I won't bother about T. So we start again. We have our Q, which starts as S, and then S can still see both A and B. S of A, we can only get 2 now from S. We can still get 5 from B, obviously. That deals with S. Then A can't see C anymore, and it can't see D because there's 0 flows, so A can't actually see anything. So this time, after B, C goes on the Q, C and D, but they're seen from B. Okay, so C actually now gets 2 from B. That won't be so relevant. And D again gets 3 from B. Now, what about C? Well, C doesn't see anything because E can't get to E because this pipe's saturated and this has 0 flow, this edge. So C is dealt with by default. Now we go back to D, and D can see both E and F. So E will get again, no, not again, E will now get 2 from D. Now that's the crucial thing. So this time E gets 2 from D. I'll write that down, the D, because it's crucial. And again, F will get 3 from D as before. That's more boring. Now what happens? Now we look at E in the queue. And you see E sees T, not F. T is seen first from E. So T will actually, perhaps I should have put it down, T will actually now get 2, won't get 3 because, well, there's only a capacity of 2 anyway here, but it will get the 2 coming up there. For a double reason, T will get 2 units from E, but E came via D. Okay, so that finishes the second iteration. The augmentation has been 2 units, so we now have a flow of 5 units, but we haven't reached the maximum flow. So this time the flow actually went this way to T. And I think I've done enough now to answer the question, because it's certainly true that a maximum flow is not obtained from the layering algorithm. So this is not true. Learning to use my arrows correctly. This is not true, nor the touchpad. That's false. So we haven't reached a maximum flow. In the second iteration, C is labelled with a flow of 2 arriving from S via B. C is labelled with 2 arriving from B, and that's correct. That's this thing we did here. So that is actually a correct statement. So this is correct. At the start of the third iteration, exactly 3 edges are saturated. That's also correct, because 2 were already saturated. Actually, no, it's not correct, is it? Because these are both saturated. Have to be careful now. So this is now saturated, and because 2 units are going down there, we've got 3 plus 2, which actually saturates this edge as well. So actually this is incorrect statement. There are 4 edges which are saturated. So as it stands, this statement is false. Now let's look and see. I have to remove, I'm afraid, the scribbling, but we have to remember that the only true statements were B and C. The other two were false. So let's see what our options are. B and C are true. That is therefore correct. See if I can mark that. That is correct. Correct answer. B was true, so the first one is incorrect. C and D are false. No, because C is true. A and D are true. No, because A and D are actually both false. So that's confirmed that there's only one correct answer. That's really what I was trying to check. 2 true and 2 false. Next page. Okay. Question about finding optimal solutions of some problem. Doesn't require any particular theory here, particularly on this multiple choice style question. We have 3 vans of different volumes and trying to move stuff, 50 meters cubed of stuff from London to Paris. Not possible at the moment, probably. So we've got to try and do this with minimum cost. Now we have to move 50 meters cubed, and for each meter cubed it costs £10. So we can't do this for less than £500. The question is, can we do it for £500? Quite a good looking solution is to just use 3 vans of size 17, and that will do the job for £510. So the question is that the best we can do, or can we do other things? So probably best here to, I mean, these questions will come in this order, so it's probably best to look at this question by question, statement by statement, I should say. So this is just arithmetic here, so you don't have to worry about vans and London and Paris and so on, you just do the arithmetic. So if we've got A vans of 7, B of 12 and C of 17 equal, total cost equal to 500, that's what we're interested in, may or may not be possible, then this arithmetic equation has to be true. A plus B plus C is 0 mod 5. Is that true or false? Well, it's pretty easy calculation. We've got A 7 vans A vans of 7 meters cubed. Well, that will cost £70 if we use those. Okay, if the V is equal to 7, it costs 10V per trip. So 70A, 120B, I don't think Hertz goes exactly by volume, but anyway, 770 times C, that's the total cost. And we're asking whether that can be 500. So that's equal to 500. Divide by 10. There's still a 0 there hidden on. Cancel that hidden one. So that gives something equal to 50. We're asking mod 5. So mod 5, this is 2A plus 2B. I just said this verbally. Plus 2C is equal to 0. Mod 5. Equivalent, I'll say, because I'm doing it mod 5. Well, it's not quite what we've asked. On the other hand, this statement means that 5 divides 2 into a plus b plus c. And if 5 divides twice something, it has to divide the something, because 2 and 5 are prime numbers. So 5 does have to divide a plus b plus c, so their sum is indeed 0 mod 5. So this statement is true. Now, that may help us find a solution. You see, if that statement is true, we're trying to do better than 510. We know 3 of these vans will cost £510. So we want to try and look for combinations of vans, A of one type, B of another type, C of another type, so that A plus B plus C is 0 mod 5. Well, obviously we need at least one van, we need several vans. So the best, the sort of smallest thing would have the sum equal to 5. So can we get A plus B plus C equal to 5? Can we sort of find solutions of that type? So here you just have to sort of fiddle around with the table, really, and see whether you can get, you don't have too many combinations to look at, you see. So let's start with the biggest number here is the 17. So let's start with the 17. I think I can get rid of all this now. Let's start with the 17. And first of all, let's suppose we have one of those. So maybe I'll do a table here. A, B, and C. Let's suppose we have one van of size 17. Okay, so that means that C is 1, and we've still got to, but only 1, so we've still got to get 5, so we might have 2 and 2, I don't know, or we might have one of them is 0. So let's see, if A is 0, B would have to be 4, so that would be 48. B would have to be 4, so that would be 48 plus 17. That's too much. So could B be 3? B would be 36, but it still won't work out. Let's try B is 2, and that would force A to be true. Actually, I don't know if I did B is 3. Maybe I should do that again, check it doesn't work. So if, let's start with B is 3, that would force A to be 1. So that would be 7 plus 36. That's 43, but plus 17 is too much. That goes bust if we're playing blackjack. And so let's look at 7. 2 times 7, that's 14, plus 24. That's, let's write this down. 2 7s are 14, 2 12s are 24. And then we have a 17, and that's still too much. Okay, so that doesn't seem to be useful. So maybe we could have no vans. So let's go back to 0 vans of size 17. I should have done that first, maybe. If I have 4 12s are 48, well, that's no good, obviously. 3 12s are 36. That would leave 14. Here we've got a solution, you see. 2 times 7 is 14, plus 3 12s are 36. So that is a valid solution. Okay, the question is, are there any others? So that already does better than the 510. So this is not the optimal solution. The question is it unique? That's what we're trying to answer for part B. Well, we go down to B is 2 now. Let's see, we could still, I think we're going to need C, but if C were 0 and B were 2, that would be 24. But then 3 7s would be an odd number, so that would be no good. So I think that's going to be no good. I think we've got to go back now to C being 2, say. That would be 2 17s are 34. That leaves 16, C is 2, 34, that leaves 16. That's not going to give any solution. So I'll abandon C being 2. Maybe, let's see, let's go. I don't know if I did them all. Did I? For C is 1. Maybe I did B is 1. Don't have any B is equal to 1 here, so let's try B is equal to 1. That's a 12. That leaves 38. 38. How can I get 38? I could get maybe 3. 3 sevens are 21. That would leave 17. I don't know, why did I miss that? I'm not sure why I missed that out. So I didn't do this systematically. Okay, this would appear to be a solution. 21 plus 12, 33, plus 17. That's a solution. Okay, so I have at least 2 solutions. It wouldn't take you long. I mean, obviously it's much easier to do it on paper. I'm afraid I'm sort of hampered doing it on the screen. But it wouldn't, you just sort of choose, you do it more systematically than I made a bit of a mess, but at least I've got 2 valid solutions with cost equal to 500. We can't do better than that because we've got to move 50 meters cubed, so we can't do it for less than that. But anyway, what have we discovered so far? We've discovered that there is not a unique solution. A is correct. There isn't a unique solution. Any solution minimizing the cost uses exactly 3 vans. Well, that's not true because these both use 5 vans. You see, the 3 vans was this idea here, but that was really eliminated by the truth of the first statement. So this is false. It's probably false because the first statement is true. Now let's see if we have enough information to answer this quiz. So A and B are true, that's not correct. B and C are false, that's correct, that's the correct answer. B and C are false, I've shown that categorically. So I don't have to bother now. Normally I would go over D, but I've spent too much time on this question. So we'll just accept that that's the correct answer. So we're fortunate here we didn't have to assess D. And things would come in that order. So if you did this question in order, you wouldn't have to worry about D. If you're worried about D or interested in D, you can look at the paper version of the question. Okay. Next page, getting to the end. So here we have a question finally about linear codes. We thought we had one in part 1, but we didn't. Now, you remember, codes can be defined in 2 ways. It's the kernel of the check matrix, which is what we've got here, or by a basis at least generated by some other matrix. So in this case, we have this, excuse me, we have this check matrix, and you need to ask yourself, is this in sort of standard form in the sense that there's the identity matrix on the right? Well, that doesn't have to be, but you can generally change the rows to get this to be true. So in this case, there is the identity matrix on the right-hand side. So this has the form which I've emphasized many times, the Sun matrix A followed by the identity matrix. Here it's the 5 by 5 identity matrix. So how many code words are there? Excuse me. The rank of this matrix, because it has the identity matrix, the rank, which I typically call R, is equal to 5. The length of the words is, no, sorry, it's not it's 6 by 6 identity matrix, got that wrong. So rank is 6. do this properly. Rank is 6. The code words have length 8, which is just the number of columns. So the dimension of the kernel, rank plus kernel, is equal to 8. So the dimension of the kernel, which I normally denote by k, which is the dimension of the space code of what's the dimension of the kernel, which is the dimension of the space of code words, is in this case equal to 2. 2 plus 6 is equal to 8. So the dimension is 2, so there are 2 to the 2 code words. So the size of C is equal to 2 to the 2. Excuse my writing. Is 2 to its dimension. I write 2 to the k, which in this case is equal to 4. So this is a correct statement. Now the minimum distance between the code words is 3. How do we find the minimum distance between the code words? Okay, I'm going to clear this, and the way I do this is I find the matrix, what I call the encoding matrix, which I do by taking the matrix A, which you can see here on the left of this line, but adding on the top of A, I add the identity matrix. Here I can only add the 2 by 2 identity matrix. So I add 1, 0, 0, 1. And that new matrix, which you see here, is what I called E. It's the encoding matrix. The identity on the top with A below. And the columns of this matrix give a basis of the code words of the space C. So because there are only 4 code words, we're only missing, well, we're missing 2, we got the 2 columns. Obviously one code word is the 0 code word, which is just 8 zeros, which I'll just write 0 underlined. And there's one code word missing, which is the sum of these 2 columns. You can get any linear combination, if you like, of the basis elements, but since we're working modulo 2, the only new element we can get is their sum, and that is the column 1, 1, 1, 0, 1, 1, 0, 1. So that is also a code word. I've written it as a column vector. Why don't I also write it as a row vector? 1, 1, 1, 0, 1, 1, 0, 1. That's a code word, as are these 2 columns here and here. Now, what is the weight of these columns? Well, this has 1, 2, 3, 4, 5. This has 5. This has 6. So the minimum distance is actually 5. Okay, it's not 3, it's 5. The minimum distance between any 2 code words is, because, for example, between these 2, it's just a matter of this minus this, but that's equal to this column, and that has weight 6. So the distance between any 2 of them, I mean, I've done it, you just have to check the weight. When you have a linear code, you just have to check the minimum weight. That's the minimum number of ones of each of the code words. Not enough to do it on a basis, actually, although here it would have sufficed, but it's not enough to, as I once said erroneously in a tutorial, it's not enough to check on a basis. You have to check on all the elements. You have to find the minimum weight. That's the minimum number of ones of each code word. But here it's 5. It's not 3. So this is wrong. This statement is wrong. It's false. Remember, this was true. There are 4 code words. Now, this thing here, is it a code word? Well, we've got all the 4 code words written in front of us. And the only one that starts 1, 1, 1 is this one here. And it doesn't continue. It continues 0, 1, but it doesn't finish 0, 1, 0. It finishes 1, 0, 1. So this is wrong. This is not right. No. Incorrect. False. Now, let's see where we are. If we're lucky, we don't have to do any more work. No, that was a bad idea, but maybe I'll remember what the answers were. So A and B are both false. So we know A is true. B is false, so this is not correct. B and C are both true. No, that's not correct because C was false. C and D are false, maybe. A and D are true. Well, we're stuck now. We have to look at D, unfortunately, because we've got two that could be. C was false, but we don't know what D is. A was true. So this is an instance where we do have to look at D because we did them in order, and we have to actually come and decide on the verity of D. Well, I shouldn't have erased what I did, but you can check that the last code word which we wrote down was indeed this one. This was a code word. This was the sum of the two columns that I got by adding the identity matrix here. So this is a code word. Okay, this is a code word. Now, is it the correction of this thing here? Well, if we look at this message, how many errors have we corrected here? We've actually corrected two. We've corrected two errors because we've converted the second 0 into 1 and the third 0 into 1, and then we get the same code word. So since the minimum distance between the code words is 5, we are able to correct two errors. So this is actually correct, this statement. This is the nearest code word to this. This is the unique code word that's nearest to this word. See, if I were to take one of the other code words, I'd have to change more than 2 bits. Let's actually do that. Let's take the code word in which I put 0, 1 on top of this second column. So that's the code word written horizontally, 0, 1, 0, 1, 0, 1, 1, 1. And let me write this one underneath so that we can actually see how many digits we had to change. So originally it was 1, 0, 0, 0, 1, 1, 0, 1. And to change this bottom one to the top one, I have to change 1, 2, 3, 4, 5 digits. So this is much closer than this code. This was a code word here. This is a code word. This is in C. But this code word is much closer than that one to that one, as will the other. It will also be closer than the other code word. So that's doing it in practice, but the theory is enough because once you know the minimum distance is 5, you know it corrects 2 errors, and this is the correction of this word using 2 errors. So this is actually a true statement. This statement here is true, and therefore the correct answer is that A and D are both true. That's the correct answer. Okay, moving on to question 20. No, we're almost there. Last question. So this is really about RSA. Actually, as explained in the paper exam, this is closer to the original version that was discovered of the algorithm by Clifford Cox, and working on using previous work of James Ellis. So I call this a Cox-Ellis algorithm. So we have to decide on the truth of these statements. And the question is actually, if you're familiar with the theory here, you should find this relatively easy, but the question is designed to help you. So we have prime numbers. P and Q are prime numbers. There are certain conditions here, but it's not so relevant. Incidentally, the difference here is that we're using the same modulo, modulo n, but we're taking to the power n. So that's the difference. In the RSA algorithm, we normally have a different exponent, often quite a small exponent compared to the product of the prime numbers. Here it's the same number. But anyway, that's not relevant to the question. So you're told that there exist integers for which this equation is true, and that's certainly correct because q and p minus 1 are co-prime. So you didn't really need this statement because it's repeated by this statement here. So you can assume this statement. And you're even helped by saying that if you multiply both sides by p, this becomes nx plus p minus 1 times something is equal to p. So we're given this equation, which will be helpful later on. Now let's just go through the statements in order. X is the inverse of q modulo p minus 1. Well, that's correct because modulo p minus 1, that cancels out and we get xq is equal to 1. So this is certainly correct. Statement A is correct. Either p divides c or c to the p minus 1 is 1 mod p. Well, p is a prime number, so Fermat's little theorem would tell you that c to the p minus 1 is 1 mod p, provided c is not 0 mod p, i.e. provided p does not divide c. So either p divides c, or by Fermat's little theorem, by Fermat's little theorem, this is correct. So by Fermat's little theorem, B is certainly a correct statement. Now, what about c to the, well, c to the p is c mod p. That's always true. That's just Fermat. I mean, if these two, either of these two possibilities imply c, because you take this to both sides to the power c, you'll get c to the p is c mod p. But even if p divides c, this is true because both sides would be 0 mod p. So this is also, I didn't really mean the arrow there, but this is also an instance of Fermat's little theorem. So this is also true. Now what about d to the power x? Well, d to the power x is d to the x, that's c to the nx. So d to the x is c to the nx. So d to the x, here I write it here, is the same thing as c to the n, because that's what d is, all to the power x. But you're told what nx is. Nx is equal to this stuff. So if you like, that's c to the power p minus p minus 1. Well, perhaps the best thing to say, and let me say it a slightly different way. Let me not put it on the other side of the equation. Let me say that c to the nx plus c to the p minus 1 let's say this is p minus 1 times py is equal to c to the p. Now, d, we have to worry about whether if p divides c. Well, if p divides c, then d will be 0 mod p, and c will be 0 mod p. So that d is satisfied in that situation. If not, this is d to the x well, if that's always d to the x, but then this is times c to all this stuff. But since we can forget the case in which p divides c, we know that c to the p minus 1 is 1 mod p. So this becomes 1 to some power, so it's just 1. And then c to the p is always c mod n. So, and if it's c, it's always c mod p, I should say. So this is equal, d to the x is equal to c mod p in all cases. So actually this is correct as well. Okay, this is also correct. So in fact, all 4 statements are correct. And this is actually one of these questions in which you have to go through them all and decide whether they're all true. And they are all true. And get rid of this and state that they're all true. So they're all true, and that's the end of the quiz. And we can check now our answers. We're only doing half the quiz. And the quiz is now working. You can check on the exam, on the mock exam, what your marks are, what answers are correct. Hopefully submit all and finish. And you see we only started from question 12, and they're all correct. Okay, so this is, as you know, a pre-recorded lecture. Please look on Keats. There will be a live session on Friday morning, plus the possibility to contact me at other times. Bye.